Hi, today we are going to do a momentum and impulse lab. In this lab, what we're going to focus on is looking at how change in momentum is equal to impulse. To do this, we're going to use this AirTrack system. We have over here a force sensor, and we have over here a motion sensor. And we will graph the motion of the cart as it's going down the track, looking at its position, taking the slope of that to figure out the velocity of the cart before and after the string stops the cart from moving. This string is attached over here to the force sensor, so as the string starts to pull back, we'll be able to measure the reaction force. Remember, every action has an equal and opposite reaction, so the force sensor will be pulling back on the cart, causing it to come to rest. As we're moving through this particular lab, we will use the Pasco Capstone software for a collection of data. So on the screen in front of you, you will see a data table. That data table is part of the handout for this particular lab. And you'll notice that we are going to do two trials. In this video, I'm going to do one trial because the process is the same with the second trial. Data will be provided by your instructor if they would like you to do the calculations for the second trial. In this particular lab, the first thing we need to do is calculate the mass. So I'm going to take the glider off of the track and place it on a balance I have here in front of me. The mass of the glider is going to be 204.4 grams. 204.4 grams. We need to convert that to kilograms, so that's 0.2044 kilograms. So you'll want to record that in your data table. The next thing we're going to do is we're going to move over and select the graphing functions. We are graphing force and we are graphing the velocity. As I mentioned, we really would like to do position and get the slope. So I'm going to switch that over there because we'll get a better graph with more averaging using the slope of the position than just using the velocity. If we want acceleration, we'd use the velocity graph. And so what we'll do is turn on the air supply and I'll demonstrate to you how this works. So the glider is sitting here on the track. I will push the glider down the track, and as you notice, it gets to the point where the string becomes taut, and it then pulls backwards on the force sensor. I'm using a string that has some elasticity to it instead of a cotton string or a high strength string. And the reason I'm doing that is it will allow the force to be elongated, and we'll get a little bit better data here. Instead of the force happening over a short time, it will happen over a little bit longer time, because as the string is being pulled and stretching, that it will apply a smaller force for a longer period of time, a basic concept of impulse. So I'm going to start recording data here. I'm going to make sure my force sensor is paired. See at the top there, it was not. And you can see the motion sensor. I'm going to validate that the motion sensor is picking up the cart. You can see the top, the blue, is dropping down. And you can see that as it's coming up behind my picture here, we're getting a nice sinusoidal curve for the position graph. So everything is appearing to work correctly. What I am going to do is I'm going to zero out or reduce the scale of the graph. To do that, I will hit record one more time, and I will use the scaling function to scale the graph down. Now, this is bouncing around. The force sensor does have some chatter in it, as well as the motion sensor, but note that this is over a very small interval. Once I start to actually apply forces, I'm going to get a very clean graph of what's going on here. Okay, so here we go. I'm going to take the glider. I'm going to hit record. I'm going to send the glider down the track. And I've collected my data. That is the data that we needed to collect. Now turned off the air supply, and we will zoom in this data so that we can see what is occurring here. The slope of the position graph is the initial velocity and the final velocity. And so we will use the slope function built into the Capstone software. I will choose a linear graph, and I will choose the highlighter. Bringing down and looking at the initial velocity of the glider on the way in. And the initial velocity appears to be, getting some of those points on the back side there, but the initial velocity appears to be negative 0.908 meters per second. I then am going to move this over to the other side, again collecting some data after the collision. And in doing that, I'm finding that my data is about 0.701 meters per second. So we're seeing a change on both sides. Depending on the data I'm selecting here, you can see I get some slightly different values, the length of the data. So understand that there is a little bit of error depending on the data set that we choose from. I'm trying to pick the data set that appears to represent the trend the best. And I'm now seeing that on the left side, the data actually might be better represented with negative 1.02 meters per second. And on the right side, this is after the collision with 0.7, we'll go with 0.701 meters per second. Now, the force sensor is also collecting data. I'm going to expand this out here so we can see what's happening. Note the force sensor does have a little bit of variation. That happens with these force sensors. They are fluctuating based on external forces, but also some of the way the software is written. So we're looking at the force that's occurring from where the hand is on the screen over to where the hand is on the screen. As we're looking at that range, we are seeing that the force is increasing in the backwards direction, and then the force is decreasing. So what we want to look at is the area of this, because force times time is impulse. We have the force, we have the time. So we can use the area tool. And again, we will highlight an area on here. So I'm going to look at it from right about there on the left to right about there on the right. And we are seeing that we are getting about negative 0.3 Newton seconds for that area. Now, note that that is only rounded to the 10th. This lab will have some error in it because our data only goes to one significant figure on the area function. There is a way to increase the number of decimal places, but recognize that Pasco is saying here that they believe that one significant figure is the best that we should be measuring to. So I'm going to ask you in your data to sort of match what we did with the velocity and use 0.337 Newton seconds. That will be the actual impulse that you'll use in your data table. And what we are going to do is we are going to figure out the change in momentum. We know the mass, so knowing the change in velocity, we're able to calculate the change in momentum. mv final minus mv initial, mass times the final velocity minus mass times the initial velocity. That will give us an area. That will give us the impulse, and then that value should compare out to the 0.337 Newton seconds. Note that the force sensor's direction is pointed one way while the motion sensor is pointed the other way, so we may have to rectify the signs to make sure that this matches. So take note of that, when you calculate it, the negative impulse one way is the positive impulse the other, because the force sensor and the motion sensor are pointed towards each other. They're not pointed in the same positive direction. What you'll do is you will now calculate out the change in momentum from the motion sensor and verify that it is similar in value to the force sensor. If you have any questions, as always, please let me know.